Hi, my name is John Kroc-Malney, and I've developed these visual tutorials to accompany any technical training format that might be delivered. In this presentation, we'll explore parallel electric circuits and how they are different from other types of electric circuits. In this presentation, there will be three learning outcomes. Number one, describe parallel electric circuit designs. Number two, calculate parallel electrical circuit properties. And then number three, differentiate among simple, parallel, and series circuits. A general review of simple electric circuits will bring to mind that they have a source of power. Simple electric circuits only have one load, and that one load offers a total resistance to the entire circuit. The amperage flow will be determined by this circuit resistance. Using the principles of fluid power, we can see the application of 120 psi pressure difference across the water circuit. Notice that this 120 psi pressure difference is also what is dropped across the circuit load, referred here to as R1. The total resistance to this water circuit is determined by the resistance of the R1 load. Therefore, the total resistance of the water circuit determines what the flow in gallons per minute will be with the difference in pressure. Notice that once determined, this GPM flow will be identical wherever it is measured in the water circuit. In a simple electric circuit, the principles are the same. In this graphic, we see 120 volts AC power supplied to one load, and that one load is called R1. This same applied voltage is also the voltage dropped across the R1 load. Using Ohm's law, we can then determine the circuit amperage. In this graphic, 120 volts AC divided by the R1 resistance of 120 ohms of the load gives us an amperage value of 1. Notice that this 1 amp of electrical flow can be measured anywhere in the circuit. You will remember that in any electric circuit, there are power sources, loads, and conductors. Here's an example of a parallel electric circuit. Notice that the three loads, R1, R2, and R3, are wired into the circuit in parallel to each other. Let's consider what happens in fluid power circuits when loads are piped in parallel. In this graphic, notice that there's a measure of 120 psi difference being applied. In parallel circuits, we can measure this same pressure difference across the first R1 load. The same 120 psi can also be measured across the second R2 load. In fluid power circuits, water flow is calculated by dividing the pressure drop by each resistance of the branch load. In this graphic, we see that the first branch having 1 GPM and the second branch also having 1 GPM. Again, what determines the flow in each branch is determined by the load resistance of that branch. Also taken into consideration is the voltage being applied to that branch. In fluid power circuits, we may understand that if we add up all of the flow rates in each of the branch pipes, it would equal a total flow existing going into and out of the pumps. In this example, 1 GPM is in the first branch, plus 1 GPM in the second branch, equals the total flow of 2 GPM. This 2 GPM goes into the suction side of the pump and leaves the pump out of its discharge side. Parallel electric circuits operate under the same principles as parallel water circuits. In this parallel electric circuit, we see an applied voltage pressure of 120 volts AC. If we measure the voltage drop across each branch load, we measure this same value. In parallel electric circuits, the applied voltage is the same as the voltage dropped across each load. In parallel electric circuits, there are 4 laws to apply to determine circuit values. The first law of parallel electric circuits states that the applied voltage to a circuit wired in parallel will be the same as the voltage dropped across each load in a branch. Using our understanding of the Ohm's law formulas, we can determine each branch's amperage by dividing the branch voltage drop by the resistance of that branch. In this graphic, we calculate 120 volts AC divided by 120 ohms in each of the branches, resulting in 1 amp each in the branch. The second law of parallel electric circuits states that the branch amperage of a parallel circuit is found by dividing the voltage drop across the branch load by the resistance value of that load. In electrical parallel circuits, there is a total amperage flow of electricity, and it is found by adding all of the branch amperages together. In this case, we add 1 amp in branch number 1 and 1 amp in branch number 2 and 1 amp in branch number 3, giving us a total amperage of 3 amps. This 3 amps leaves and goes into the source of the power. The third law of parallel electric circuits states that the total amperage is the value of the amperages existing in the branches, or amperage total equals the branch 1 amps plus the branch 2 amps plus the branch 3 amps, etc., etc. Let's step back and review what we've learned so far. In series circuits, the total resistance of a circuit was added together with the resistance of each particular load. This total series circuit resistance then determines the amperage flow as a result of the pressure difference of the voltage. In series circuits, the greater the total resistance, it results in the lower amperage. In parallel circuits, we see that for every load we place into the circuit demands its own flow. Applying logic to what is happening when additional loads are placed in parallel, we see a total amperage existing and this amperage being split among the circuit branches. In this graphic, we can visually see the differences between series and parallel circuits. In series circuits, adding more loads increases the total circuit resistance and therefore reduces the amperage. In parallel circuits, when additional loads are placed in parallel, the total amperage increases to handle this extra work. In parallel circuits, when more loads are placed in parallel, the amperage increases. Therefore, the total parallel circuit resistance has to become lower. In series circuits, the more loads placed in series, the lower the amperage flow due to the higher total resistance. In parallel circuits, the more loads placed in parallel, the higher the amperage flow due to the lower total resistance. The calculation of total resistance in parallel circuits can be done 2 ways. The easiest way is to observe Ohm's law for discovering total resistance by taking the applied voltage and dividing this by the total amperage. In this example, we see an applied voltage of 120 volts AC divided by a total amperage of 3 amps. Doing the math, we see that the total resistance calculated to be 40 ohms, even though we have 3 loads, each measuring 120 ohms each, wired in parallel. A second way to calculate resistance total in parallel circuits is by using this formula: 1 divided by 1 divided by the value of the first load, added to 1 divided by the value of the second load, added to 1 divided by the value of the third load. In this graphic, we see how the measured elements are entered into the parallel circuit total resistance equation. Just like our value we arrived at when we divided the circuit's applied voltage by the total amperage, we calculate 40 ohms using this second mathematical method. In our review of parallel electric circuits, there are 4 laws used to calculate the properties of the circuit. Law number 1. Applied voltage is equal to the voltage dropped across each load. Number 2. Amperage in each parallel circuit branch is equal to the voltage dropped across that load divided by the load's resistance. Law number 3. The amperage total is equal to the amperages in each particular branch, or amperage total is equal to the amperage of branch 1 added to the amperage in branch 2 added to the amperage in branch 3. Total resistance in a parallel circuit is equal to the voltage applied divided by the total amperage, and by dividing 1 divided by 1 divided by the first load value plus 1 divided by the second load value plus 1 divided by the third load value. In reference to parallel electric circuits, these 4 laws will be used to calculate and measure each component making up the parallel circuit. Parallel electric circuits also consume power when sources of power are connected. Notice that in parallel circuits, we see full power of 120 volts being applied to each load of the branches. Each load, R1, R2, and R3, receive this full power of 120 volts from its supply. We can then calculate the wattage of the circuit by referencing the wattage formulas. In parallel electric circuits, the total wattage is made up of loads involving 3 branches and each branch using 1 amp each. Adding up the branch amperages, we see a total of 3 amps being supplied to the circuit from its source of 120 volts AC. The total wattage of the circuit is the total amperages multiplied by the applied voltage. In this example, 3 total amps multiplied times 120 volts applied to the circuit gives us 360 watts total consumed by the circuit. We can also calculate the individual branch wattages by applying this same formula to a specific branch. Using branch number 1 in this circuit, we see 1 amp being initiated in a circuit that has 120 volts being applied. We calculate branch 1 wattage by taking this 1 amp branch flow and multiplying it times 120 volts supplied to it, giving us 120 watts in branch number 1. Notice that branch 2 and branch 3 in this example will have the same wattage value of 120 each. The total wattage of this parallel electric circuit is 360 watts, found by adding up each of the branch wattages. In series electrical circuits, the more loads we place in series reduces the wattage of each load. In parallel electric circuits, each load gets its full share of voltage and as a result consumes the higher wattages. This is why in parallel circuits, light bulbs are brighter. More wattage is being consumed. When wired in series, light bulbs are dimmer. Less wattage consumed in these types of circuits.